So imagine that it's 200 years ago, almost exactly. And scientists have now started to discover, they don't realize it yet, but they've started to discover the quantum realm. Okay, I'm going to use that terminology a lot over the next little while. I should make sure you're clear. Do you guys know what I mean when I talk about quantum? Quantum means microscopic. We're talking the stuff that we can't see, right? I just finished talking about this intangible stuff that we know exists. It has to. But can we actually see an electron? No, it's not possible with the technology we have. It may never be possible. And so we're now starting to work on the subatomic particles, protons, neutrons, and electrons. Scientists didn't even know about those at the time. We haven't got to the timeline yet here, but the electron, if you look at the timeline right here, J.J. Thomson didn't discover it until 1897. And yet here we are doing a course and a unit all about electricity. And isn't electricity the movement of electrons? And yet scientists didn't even know what electrons were for another, 77 years. Right? Hans Christian Ørsted is working and playing around with electricity and magnetism. Guys, please. And he was trying to figure out whether electrical current was similar to magnetism. You guys can see that. And I've mentioned before that electricity and magnetism are not one and the same, but I kind of lied. We're going to get towards the point where we talk about EMR. We're going to get there. EMR wasn't discovered till later, but maybe you know this name. It's called electromagnetic. You guys know the R? Radiation. I'll just stop at radiation if that's cool. Okay. And so we're actually discovering that these are kind of one and the same, but what I want to make sure is clear is that there are some separations though. Positive and minus do not have any correlation north and south. Okay. They are still independent, but scientists are starting to discover that there were so many similarities between these things. What I want to do right now is I want to show you an experiment that Hans Christian Ørsted did in 1820. I didn't have the apparatus for us to try this yesterday. I don't have the stuff that makes it work. But more or less, he was doing what I tried to have you guys do. He was playing around with materials, moving things, putting a compass nearby, running electricity through things, and just kind of discovering what happens. So let's watch this short little YouTube video here, and then we'll talk about it. So this is what I didn't have, right? Sorry that it's so dry. Let me just pause with that last thing there. He was discovering how electricity and magnetism go together. And if I can kind of just find you this picture right here just to explain this. I don't have the ability to make this work. And one of the reasons why is that in order to actually make this compass needle move, you need a lot of current. And the little voltage boxes that I gave you guys there, they max out at 2 amps. And anything more than that just isn't really safe for us to use because amperage is what causes you to have, like, say, heart problems. Like when you do the zzz thing to try to make your heart defibrillate. You need a lot of current. Anyways, long story short, I couldn't safely give you that much current. Here's how the experiment would have worked, though. You take 2 basically objects here. These are connected up to electricity. And you touch them on a wire. need a lot of current. And what ends up happening is over here would have been north. This needle was pointing north. And as you hook up the electricity, it all of a sudden makes the compass needle move. How many of the little stations that I had you guys work on yesterday did you have something similar to that where electricity caused a compass needle to move? And that's what I want to get into in our discussion here, is that this was the first time that scientists started to recognize the relationship between three things. I like to draw it in one of these like triangles, like this. I think this helps frame things really nicely. One is that sometimes we need electricity. And if I use E with a little arrowhead on top, you guys okay with that being like an electric field? So you need something electrical happening. We also need something magnetically happening, which is the B in the triangle. And what that usually ends up causing is some sort of motion. And many of the stations that we had involved different things happening. Like, for example, there was one over there on the side wall there. Right? Did you guys see the little wire move a little bit? It wasn't a lot, but if you had electricity and if you had a magnetic field, you could make something move. There was one at this table over here where I gave you a coil of wire and I gave you a magnet, and I asked you to move the magnet inside the coil of wire. And so what happened is if you took a magnet and moved it, you made electricity. These are the things that we're kind of starting to explore and figure out the principles of. But again, this is really challenging to work with because can you see an electric field or a magnetic field? Well, you can see the effects of it, but it's really hard to internalize. Anyways, let's move on here. So this starts in 1820. Hans Christian Ørsted basically discovers this experiment, and the key words are that it used to be parallel, the compass used to be parallel, and he could get it to move perpendicular. So this is a word we're going to use, and it has two uses in our class. It's the word induction or induce. We've used the word induction before to describe the concept of how if you were to have an object that was neutral, that like used to look like this, where it's kind of evenly spread out. Induction is where you make like all the positives go to one side and to the negative side. That's one use of the word induction, but induce is another word that we use. Induce means to create or to cause. I think that's kind of the idea behind the word induce, right? Like if I induce something to happen. Personal experience with this one. Anybody ever heard the word induce labor for like someone needing to have a baby? You've heard that phrase before? My wife works in that field, right? To induce labor means that you're going to try to find a way to cause the mom to give birth by usually like giving medicine, breaking the woman's water, something like that. So anyways. So in this term right here, induce, basically means that we're going to cause something to happen. And the three things that are happening here, again, are the magnetic field, the electron flow, and some sort of motion. Okay, let me go on to the next page here. Before we go too far into this, though, we need to make sure we've covered the concept of current. Because unlike in previous sections, we don't want to just have one or two electrons. We need to have a lot of current. We need to have all of these electrons moving at once. And so we typically need to measure this in coulombs. Hopefully you're kind of familiar with the concept of a coulomb again. A coulomb is a lot of electrons, right? I think it's like 6.25 times 10 to the 20-something electrons. It's a grouping of electrons. We need a lot of them often for us to notice this. Okay? The units for current are called amps, if you haven't heard that before, and it's measured in coulombs per second. Long story short, if you have more electrons, you have more current. It's kind of the speed at which the electrons are moving, but it's not really the speed, it's more about how many of them there are. Okay? And then here's the formula if we ever need it. Okay? I is equal to Q over T. How much you have per time is your current. Okay. Another little side note before we go a little further into the experiments, we have to discuss, in case it comes up, electron flow versus conventional current. Remember the talk we had about how Ben Franklin thought that positive charges moved? You know, eeny, meeny, miny, mo, positives move. He didn't even know they were positive, I think. They could have called them A and B for all we care. And then later, once electrons and protons are discovered in the 20th century, we realized, shoot, protons are tied in the nucleus, electrons move, right? Long story short, you may see the word conventional current. Conventional current was used for hundreds of years, from probably about 1750 until my guess is about the early 1900s, because the prevailing thought at the time is that positives moved. So if you ever see the word conventional current refers to how a positive charge would flow, except positives don't flow. But if a positive charge could flow, positives would always go from positive to negative. Let's say, you guys know batteries? I should talk about that for a second here. This is also really good overlap for Chem 30. say you have a battery that has like two sides of a battery here. One side's positive, one side's negative. And then you run some sort of wires around in some sort of loop. This is a horrible loop here. Which way does the electrons flow? Electrons go from the negative pole to the positive pole. So I'm just going to label this real quick here. In purple, this would be what, like that. This is what electrons do. Electrons go from negative to positive. If you know your vocabulary, does anybody know the vocabulary for negatives and positives on a battery? What do we call them? Yeah, good. Anode and cathode. Yeah. So a lot of chemistry overlap here. Anode and cathode. So your electron flow goes from negative to positive because that's what actually is happening. Well, for years, conventional current, people thought that the flow of particles actually went the other way. They thought it went this way here. And so we still sometimes see things called conventional current. Now, I don't think they called it conventional current at the time. I think they just called it current. They just didn't know that it was wrong until we later discovered subatomic particles. Does that make sense what I'm saying here? So, too long didn't listen version, I guess, because I got off of my soapbox there. If we're talking electrons, which are what actually move, they always go negative to positive. But if it comes up and you ever see something with conventional current, that goes positive to negative. Okay, so that's more or less what this slide right here is kind of showing you here. Conventional current is actually the opposite of what actual electrons do. Okay, here's the video I showed you on Ørsted, so let's move on here. At this point here then, scientists are starting to discover these new forces. They're really discovering what's not just a magnetic force, what's not just electricity, but putting it together, they're discovering the electromagnetic force. For those of you that were at the back station right there, I did an experiment where there was a moving, remember how that little triangle was right there? There was motion of a magnet. Well, that was actually causing, believe it or not, electricity. Yeah. We can't see it, obviously, because there's like no sparks. Remember that station in the back there where you were like dropping a magnet through a copper pipe? Or you were dropping magnets down those little rods there? Okay. With what we had happening, we had moving magnets. We were actually causing electricity inside that copper. And that electricity was actually what was slowing down the falling magnets through what we now call the electromagnetic force. That's what we're building towards here. In order to then help try to figure out how to quantify, that's not even the right word, in order to try to figure out how to like get a mental picture of what's happening here, we've developed some rules to help keep track of those three things: motion, fields for electricity, fields for magnetics. And this is the part of the unit that kids hate. We call these our right and left hand rules, and they're kind of little hand signals we use to try to keep track of what's going where, because we can't always see it. Okay? Sorry, you're going to hate this. Everyone hates this. You've probably heard of this even from other students before. I'm so sorry. This sucks. Okay, here's what you need to know. If you ever work with electrical current, all the rules that I'm going to show you, use your left hand. If we ever talk about conventional current or a positive charge, though, use your right hand. Here we go. Please don't feel like you have to understand this at the end of today's lecture. This takes a while. Oh, one more thing here. Before I get to the next slide here, we also try to draw things on paper that are in two dimensions, but clearly we have both an X, a Y, and a Z direction, and on paper it's really hard to draw things in X, Y, and Z. So another convention you need to be aware of, if you ever see a dot, it means something is coming out of the page towards you. If you ever see an X, it means that something is going into the page. Okay? Like if you were a pretty good artist and I was trying to draw like, something on a table, I don't know, I'm a horrible artist. I can do good physics objects. Right? Imagine that something was trying to go in the X direction. That's a good X direction. Here's a good Y direction. But like maybe that would be going into the table. But doesn't that kind of also look like maybe it's just going up and down? So what we might draw is instead of trying to draw the Z direction that way, we just might use an X. And an X means it's going into the page. A dot means it's coming out of the page. It's just a nice notation to keep track of things. The logic is actually based on an arrow. If you can imagine the tip of an arrow coming towards you, that's coming out. and if we had like an X as like the tail feathers of an arrow going into the page. Okay, anyways. Okay, let's talk about our first hand rule. Okay, here's what scientists have now slowly but surely been piecing together. Let's say that you have electricity moving. Remember that three thing that I talked about before? I'm going to draw it a lot here. The three things you need: electricity, magnetism, and motion. If you have both motion and electricity, you can actually create a magnetic field. Okay. This was actually what Ørsted discovered in his experiment. As soon as he put the electricity on in that wire, it caused the compass needle to move. What we've discovered is that every single wire with electricity in it actually has a magnetic field, and it actually goes around in circles. Okay, it actually goes around circles. I forgot to grab this before my lesson. Give me 1 sec. I have a little demo I want to show you. I forgot to grab this one first. Where is it? Here it is. All right. Sorry that I wasn't prepared. You guys know what this is? Yeah. So you use this in construction when you want to try to find a stud in a wall. So, I mean, here's a wall. As I press the buttons and I run along it, eventually I might see this button go off right here, and a stud in a wall is like where the braces run up and down. Okay, now that's not what I care about. This particular stud finder, however, has a second little button on it. Can you guys see how it says AC with a little electrical bolt right here? This one's advantage is that it also can tell whether there are wires nearby. Because if you're planning on drilling into a wall, first of all, you probably want to hit a stud, right? That's actually a good thing. But we also don't want to drill into a wire. This thing right here will tell you whether there is a wire nearby. How? Wow, that's magical. Well, it actually uses this principle right here. All wires that have moving electrons in them actually have a magnetic field running around it. Watch this. I've got a magnet right here. I'm going to turn on the stud finder, and I'm just going to wave the magnet nearby. Hopefully, the little AC button's going on there, right? What I just did there is the stud finder, you know what it actually does? Not only does it determine the stud, but it also knows if it finds a magnetic field. And as soon as it detects a magnetic field, it throws that off, right? Well, a wire actually throws off a magnetic field. This wire right here that has electricity on it is actually throwing off a circular magnetic field. Here's why this is so hard to understand. Can we see the circular magnetic field? No. And you know what? Maybe the best thing we could do to show you would be to have a wire. You know how I had one of the stations, you had like a piece of paper on there, and I had you sprinkle those iron filings on it? Maybe we could see it by like how the iron filings would go in a circle, but like that's hard to do every single time. Hence the rule. Okay, here's how the rule works. Your thumb is intended to be the direction of electron flow. So you take your left hand, because we have electrons flowing. You take your thumb and you wrap it around a hypothetical wire. So imagine that this right here is a wire with electricity running through it. Your thumb is the direction electrons are traveling. We've discovered that magnetic fields run in circles around it. So inside the wall right here has got to be a wire somewhere, right? What's probably happening is as the wire runs up the wall, there's a magnetic field running around it. And as I take my stud finder right here, it'll read the electrical reading if I manage to find... I thought I found one, actually. No. Apparently I've only found studs. But if there was a wire inside there, I should be able to make it work. There has to be a high amount of current, though. Okay, if there's not enough current, we won't notice it. But like I said, I can actually set this thing off by just... Oh, hang on. Here we go. By just waving the magnet by it. Isn't that cool? If I wave... Hopefully this doesn't work. If I wave an eraser behind it, nothing's happening, right? So clearly the magnet's doing something. So... Where'd that pen go again? Okay, so the whole goal behind this then is to be able to make a prediction as to which way the magnetic field is going. Here's what this means. If you were standing right here with a compass, your compass would point that way, because the compass points in the direction of the magnetic field. But if you were on this side of the wire, your compass would point that way. If you were on this side of the wire, your compass would point kind of into the page. And if you were kind of behind the wire, the compass would point that way. Your compass would point a different direction depending on where you were, because the magnetic field is going around in a circle. This hand rule helps us kind of orientate ourselves with that. Okay. So here's another picture of this. Now, this is a picture I found online to kind of illustrate the point, though. Look what hand this person is using. That's your right hand, which means this is a hand that's trying to describe what conventional current is. So if we had to figure out which sides of the battery this is coming from, this must be the positive side of the battery, and this would be the negative side of the battery, because conventional current is hypothetically what a positive would do. A positive would go from positive to negative. Again, positives don't actually move, right? But this would be talking about conventional current. We'd be using our right hand, wrapping it around a wire. So just as kind of an example, imagine that this right here was that wire, right here. If I were to put a compass right here, it would point that way. Take that same compass, put it right here, it would point into the screen. Take that same compass, put it right here, it would point towards me. And take that same compass right here, put it on the, what is that, your left, it would point out at you. It always goes in a circle. Very conceptual, hey? Hi. Good. Let's talk about that again. We should refresh that real quick. How do we define a magnetic field? A magnetic field always points towards south. Yeah. So all of these magnetic fields are pointing towards south, but what does a compass do? A compass points south, actually. The needle on the compass, if I could draw a compass like right here, the needle on the compass, this would be then the north side of the needle, that would be the south side of the needle, and it's pointing south. Does that make sense? Yeah. Yeah. Okay, that's the whole point of your hand then, right? Because it's either going to go clockwise or it's going to go counterclockwise. Anybody at that station over there, did I show you what happens when you like flip the two wires around? Well, if you flip the wires around, what ends up happening is rather than the electricity going, say, up and therefore going clockwise, the electricity would then be going down and therefore be going counterclockwise. So the whole point of this is to use your hand to figure out whether it's clockwise or counterclockwise. So this particular one here, it must be because of conventional current. That's why they're using their right hand. But in this case right here, it's going clockwise. No, that's counterclockwise. But if I were to have the conventional current go the opposite direction, you'd then take your hand, you'd flip it upside down. And then if, like, just look at your hand here, right? This is currently clockwise. And this is currently counterclockwise in terms of how my fingers rotate around. Very abstract, eh? Very abstract. Oh, here's another picture, but like I have as many pictures as I can find in here. Pictures do as good a job as I can, but this is a hard topic here. Okay. Let's try a little just practice experiment, see whether we kind of get the concept here. Here's a current carrying wire. Let's say that I were to take a point to the right of the wire, so randomly over here is point P. If I were to take a compass and put the compass right here, which way would the north needle of the compass point? Let me give you some possibilities. Right here, the compass could point up or down, left or right, or I could have it go in or out of the page. Those are your main possibilities. So I could take my compass and I could hold it like this, or I could also hold it upwards as well. Okay, what does an X mean? Current is going into the page. So this is my best representation of a wire that's going into the page. If it's going into the page, let's call it electron flow. Let's use our left hands, because like 9 times out of 10, you're talking electron flow. Once in a blue moon, we'll actually pull out the whole conventional current. So let's make our finger go into the page with the left hand. Based on the direction that this is going, this is clockwise. So based on our perspective, we have a counterclockwise field. You know why this is messing with me? Because from this direction is different than if I hold my hand like this. You get what I'm saying here? Right here, this is coming towards me. I see this as clockwise. But you guys see this as counterclockwise. That's why this sucks. It's so hard. Okay, anyways, long story short, point your finger into the page. Hopefully you can kind of get the idea about it. It's going this direction here. So at this location right here, if I took a compass, and if I took the compass and I faced it like up and down, the north needle would be pointing up. So if I had my compass flat right here, nothing would happen. But if I took my compass, held it like this, the north needle of the compass should be pointing straight up and down. Which is weird because north is over there. Okay. Hopefully that made sense. Okay, second rule. This was a station that was at the desk that Tayson's sitting back there. There was like a wrapped coil that we did as well. What scientists discovered is that if you have a wrapped coil of wire, you can have the same thing happening. Okay? Let's say that you have, here we go, some electricity, and let's say that those electrons are moving. These two things can cause a magnetic field. And what you hopefully discovered is that if you took the compass near that wrapped coil of wire, the compass kind of behaved oddly. Here is a rule that physicists have discovered that kind of just helps keep track of which way things are going. Okay. First thing you got to know is that your fingers wrap in the direction that the wires are going. And a lot of kids, they struggle with this concept at first. Let me do a demonstration. Here is like a core. Here is a wire. There are two ways that I can wrap something. I can go over the top and around like this. See how that's one way that I could wrap something? Or I could go under the back and then around. And the way in which you wrap this makes a slight difference. I'll show you that one more time. We'll do it from your perspective. Here I'm going to start wrapping my wire over something. If I go over and then around, that is slightly different than if I start on the back side and wrap around this way instead. So a lot of students, they really struggle with that. Okay. Our goal here is to use your fingers, and your fingers are supposed to wrap in the same sort of way that the electron flow is going to go. So in this particular picture, this wire here must have been hooked up to the anode, which is the negative pole, and the electrons are flowing from the negative through the wire around the top, over the back, and eventually the electrons will flow through here around the back, and then it would go to the positive pole, which is the cathode. Okay. Here's what this means then. If you wrap your fingers in that direction here, your thumb is the direction of the magnetic field. Okay. What that means is that your field is actually pointing this direction here. What does a field point in the direction of? Fields point towards south. Does that make sense? We talked about that? So over here, there's kind of like a pretend south over here. The reason why there's a pretend south over here is that this is the north end of an electromagnet. Did anybody on that station right there kind of discover that if you hooked up electricity around the coils, you can make an electromagnet? Okay. If you were to make an electromagnet with a bar in the middle of it, your thumb is the north end of your electromagnet. Your palm is the south end of the electromagnet. What makes this so frustrating is that your north is pointing in its field towards a hypothetical south way over here. And so your compass should have been pointing away on this side right here, and it should have been pointing towards on this side right here. Did any of you kind of discover that if you put the compass around that coiled wire? The name for that thing, by the way, is called a solenoid. It's a coiled up wire. Okay. What's useful about a solenoid is unlike that station over there where you have a single wire, if you wrap a wire around a lot, we can shove a whole bunch of wire in one small little location. We can greatly magnify its strength. And so that's how you make an electromagnet, is each loop strengthens the field. Okay, so let's try an example on this one right here. Well, actually, no, this one gives away the answer. But let's just try practicing it here. Let's say that you had an iron core, and then you're going to wrap some wire around it and make it into an electromagnet. If we want to make a prediction as to which way is north or south, here's how we do that. First, I got to find a way to wrap my fingers, and this is hard. Like you're sometimes like doing weird stuff like this. Okay, I'm going to use my second finger as my guide right here, and I'm going to have my second finger be running over the top of this object. So if you can kind of imagine that this is the bar right here, my second finger is kind of running over the top. And see this little loop around the back there? That's my second finger doing this. That kind of gets me set up. Furthermore, see how my pinky is kind of sitting way back here? That's the spot right here. Okay. So once I kind of figure that out, which way is my thumb pointing? Awkwardly into my body, that's the north end of the electromagnet. Why is it the north end of the electromagnet? Well, because my thumb is actually a field, and fields point away from north towards south. There's kind of like a hypothetical south over here. And again, that's why this is so abstract, because is there actually a south pole over here? No, there's not. but the field points away and towards based on that. And so a compass right here should be pointing that way. A compass right here should be pointing this way. Right here, it actually loops around in a circle. That was my worst drawing ever. But it actually loops around in a circle, and it actually points this way for a while. Okay, so another one just to kind of practice this. Let's say that this diagram right here, the negatives were heading down, so the electrons are going, well, see, this is why I don't like this picture, look. Because here, there's a positive right here, and there's something leaving out of the positive. Is that electron flow? No. So I think what we need to do on this case here is this is a picture that is intended to be conventional current. And it messes with you because you got to figure out which one is which. But if something's leaving out of a positive pole, it's not an electron. So we should use our right hand. Okay. So I'm going to take my right hand. If you can kind of envision this, imagine that there's like something here to wrap my hand around. I'm going to take my pinky finger right here. I'm going to wrap my pinky around it like this, and this is kind of me wrapping. Okay. Which way is my thumb pointing? Over here. So that's why if there was like a bar in the middle of this for an electromagnet, this would be north pointing that way. Can you guys see why I hate teaching this lesson? Why students hate trying to understand it? Yeah. Yeah. So let's say that there was a bar inside of it right here. This is now an electromagnet. This would be the north end of the electromagnet. This would be the south end of the electromagnet. And what it means is that a compass right here would point away, because compasses point away from north. And right here, this compass would point towards south. Whenever I draw the compass, I'm always pointing it as though it's the north needle pointing. Because remember, north actually points south, which is why Santa lives actually at the South Pole. Okay. Yeah. Fun and stupid, yeah. Another question? Okay. Okay, I've got more pictures here, but I feel like I'm kind of hitting the nail over too many times here. So let's move on to the third hand rule. Okay. The third rule is actually two rules. There's a rule for a wire, and there's a rule for a free-flowing particle. Okay, stay with me here, people. We witnessed actually this wire over there on that far station over there. Okay, if you have a magnet, you put a wire inside the magnet and turn on the electricity. Again, you have 2 out of the 3. We turned on electricity. There was a magnet nearby, and it caused the wire to like move one little bit. Okay. Now that wire that was over there on the far wall, did it move like a lot? Well, no. You know what would have got it to move more is if I wrapped it in a circle. That would have been a lot more effective. But hopefully you did see it move a little bit. We want to try to find a way to make a prediction as to which way this wire is going to move. Is it going to move left? Is it going to move right? Is it going to move up? Is it going to move down? Right, we want to make a prediction. So here's how the third hand rule works. Okay. Your fingers indicate the direction of the magnetic field. Okay. Which way do magnetic fields always point? South. So long story short, your fingers like this always point them at a south pole. Okay. Your thumb is the direction of anything that's moving. Okay. In this example right here, I've got just one random electron moving. But if you have a lot of electrons moving, like your electricity moving, your thumb is the direction that electricity is moving. Okay. Your palm then is the direction that the electromagnetic force causes something to get pushed. Okay. And so there's actually like a force that causes the wire to move. I'm going to go back to this slide right here and try to use this one here instead. Okay. So if you guys can kind of picture this, there's a wire. I know that I'm supposed to use an X for something going into the screen, but can you kind of imagine that this is a wire going into the screen? Does that kind of help? They kind of drew it like this, but they're really meaning for this to be a wire going into the screen. Okay. In terms of my hand definitely has to point towards the south. Okay. Because the field is going from north to south. So this wire right here, this wire is either going to go up or down or left or right. It can't go in or out though, right? Because isn't the wire itself already going in or out? Okay. So here's the wire. I'm going to take my fingers and point them south. My thumb is going to be the direction of electron flow, which appears to be going into the page. Which way is this wire going to deflect? Up. This picture right here, the answer would be fingers pointing south, thumb going into the page, this wire would actually deflect in an upwards direction. But let's say we flipped around the electron flow. Remember how on that station over there, for some of you, I flipped the current around? If all of a sudden, fellas, please, this is like the 5th time I've asked you to kind of not. Okay, I'm delivering a lecture. It's really disrespectful, fellas. Okay, let's say we flip the electron flow. Rather than the electrons going this way, what if they went this way? Sorry. So again, wire is going in and out of the page. My fingers still have to point south though, right? But now if the electron flow is coming out of the page, now this wire would get deflected down. And all I got to do is just flip the electricity. What would happen if I flip the north and south magnets around? Well, rather than pointing my fingers this way, this is awkward, I'd now be pointing my fingers this way. And so rather than it being deflected down, it would get deflected up. It's awkward. It's frustrating. Okay. So now this can work for not only a wire, it can also work for just a single particle. It doesn't matter whether it's a whole bunch of charged particles or one electron. I like this picture better because it's not quite so awkward. Here's what's happening. We're shooting an electron kind of in the, I don't know, downwards. Oh, that's not a pen here. We're shooting an electron in this direction here. The direction that it's originally moving is my thumb. I'm pointing my fingers towards the south pole, and based on that orientation, this particle here that was supposed to be going on this path right here will now start to get bent downwards, just like the wire kind of you saw get moved. Let's kind of fast forward here. I've got lots of pictures here, but I don't know that any more pictures really happen. I like this one here. I don't mean to be offensive, but this is frustrating, isn't it? Like, I don't care whether you're in English. I don't know what characters those are, but like, this is hard. Okay. Please don't stress if you don't get this right away. If it's okay with you, I'll ask you permission, but when you're trying these questions here, I found that it just works if you just let me literally take your hand and orientate it for you. So if you're comfortable with me touching your hands, I'll help you with this at first, because it sucks. Okay. Now, there's one last thing that we can do. There are 3 rules then that govern the laws of electricity, magnetism, and motion. We actually can do some calculations with it. We don't do a lot, but we have 2 formulas we use. Okay. Here are the formulas, and I'm sorry these are so fuzzy. This is the magnetic force, but I don't love that they use the word M, because M implies that it's purely based on a magnetic. I really think this M should be electromagnetic. But to be fair, we actually haven't really discussed the theories behind electromagnetism yet. Again, in 1820, when people were discovering this, they were still in their infancy. We now understand it to be the electromagnetic force, but anyways, they just call it the magnetic force. Okay. The magnetic force is based on 3 factors. 1, B, how strong your magnet is. If you have a stronger magnet, wouldn't you have more force? Does that seem logical? Okay. This right here, it doesn't look like it, so I'm going to write it differently. That's the letter L. L stands for length. Length meaning how much wire do you have inside the magnetic field. If I can go back to a picture here, let's say that you have, where's a picture of one of these here? See how there's a wire inside the field? The more wire that's inside the field, the more force there would be. If you only have a little section of wire inside the magnetic field, that's not going to do a lot. If you have a huge magnet and you have more wire, you'll get more force out of it. So that letter right here is L. It stands for length of wire. And then this first letter right here is an I. It stands for current. Remember what current is again? Current is how many coulombs are running per second. If you have more electrons running, you should have more force, logically. Okay. So this is one of our formulas. The amount of force that you get in your wire is the current by length by magnet. But what if you don't have a wire? What if you just have like 1 electron? 1 electron can still be deflected. Its formula is this. Q, which is the charge of the electron, V, which is the velocity of the electron, and then again the magnet. Okay. So I'm going to sit down for a bit here. The last thing we're going to do is a couple of math equations now. I don't know, I don't think these are overly taxing. I hope they're not, but if they are, I'm sorry that I made it seem like this should be really easy. These are the 2 formulas we'll work with. Before I do that, though, I need to point something out. It's highly likely that you're going to be asked to do this in the context of dynamics. You guys remember the unit of dynamics? Dynamics is all about forces. And so there are things like the force of gravity, the normal force. Sometimes we have centripetal force. Sometimes we have the force of friction. Well, this new force is the electromagnetic force. And often what we do is we make some of these formulas equal to each other. You ever done a scenario where I asked you to make, say, like the force of friction equal, I don't know, the normal force? Or maybe the normal force equal the force of gravity, and you have to kind of build your own formula. That's what we'll often be doing in this section, is we'll be taking, I usually like to write it like this. We'll either be taking the electric force and making it equal to gravity, or making it equal to magnetic, or making it equal to normal force, or maybe even making it equal to centripetal force. But we'll likely be taking some combination of forces and making them equal to each other. It just depends on the scenario. So let's try one. Very simple question. Let's say you have a piece of wire. It's 3.45 meters long, and we place it perpendicularly. By the way, I should talk about perpendicular. Let's say that I have a field that looks like this. So here's the north and south end of a magnet. I can't run the wire in this direction because that's the direction that the field is already traveling. I either need my wire to be traveling either up or down. That would be valid. Or I could have my wire traveling like into the page. Does that make sense to how I say perpendicular? But I can't have it be parallel because the north-south is already accounted for. It either needs to be the up-down or the perpendicular. So just to make this picture look a little bit nicer when I draw it, why don't I draw it so that north-south is going in the x direction? Why don't we make it so that the wire is traveling in the y direction, up-down? So here's our wire traveling up and down. And just to make it simple, why don't we just hypothetically make the electron flow being going up? Which way is this wire going to move? Okay, it can't be left-right. Left-right is already the north and south. It can't be up-down. Up-down is the current. So it's either into the page or out of the page. Okay, let's make this electron flow here. Take your left hand, point it towards the south pole with your palm up. This wire, in theory, should come towards us. Your palm is towards you. Okay, so your fingers would be towards the south, your thumb would be up. This wire would kind of come towards us. Okay, now I don't actually care about that theory. Let's do the math now. The amount of force which with this would come towards us is based on I, L, and B. So this one's fairly straightforward. Your current was, no, actually I work backwards. We're looking for current, I take it back. Current then will be equal to F divided by LB. So just plug some numbers in. Force looks like it's 1.884. Length, by the way, the length of the wire, you only get to count the wire that's inside of the field. The field would be right here. Does that make sense? This is the direct region of influence from the north to the south. Yes, I know there's kind of a field that kind of goes around over like this, but like really this yellow section is the only part of the wire that is like directly inside that north-south field. So even though the wire itself could be really long, we only get to count whatever little snippet of it is inside. So apparently, according to this question stem, we have 3.5 meters, 3.45 meters of length inside that field. And the field strength was 129. So 1.884 divided by 345 and 1.29. I got this as a final answer, 0.42, and that's current. Current is measured in amps. That's not an overly hard question, hopefully. You're probably not going to get something that easy, but I'm just kind of working our way in. Yeah, for sure. Yeah, you want me just to leave that up there for you for a second? Just want the stem here. Oh, like I need to go back to here? Yeah, okay. It's ILB if you have a wire. Any other questions before I keep moving? Okay, let's try another example. Let's say that the wire is not perpendicular. This is a rare exception. I'm not even going to do the whole example, but let's say that the wire is not perpendicular. Let's say that the wire goes in at a 67-degree angle. Take the same scenario that I have right here, and I don't know that if I can select this. Take this wire right here. What if it's not perpendicular? What if it's at a bit of a tilt? Well, we don't get to count the full amount because it's not straight on. We have to count like the tilted section. Well, you know what? We're really just using trigonometry. That's all, because the wire is no longer straight through the field. The wire is now along more of a hypotenuse. So if this ever comes up, this one's not written on your data sheet, but you would take the exact same formula and times by the sine of theta. That's all. The sine of theta basically meaning that this tilted wire right here, say I were to draw a triangle out of how I tilted it, and here's my angle. This is the actual wire in the field, right? This is the actual hypotenuse of wire in the field. But the portion of it that's actually traveling in the y direction is this section right here. Can you see how this is a hypotenuse and this is an opposite to an angle? Opposite and hypotenuse are sine. So if it comes up and you tilt it a little bit, you just throw on a sine theta. That's it. This is not on your data sheet. I have never seen it on a diploma. I have seen it in the textbook. So I don't think it's likely, but I just wanted to point that out. So, sound good? Okay, let's try another example here. Okay, let's say that you have 2.6 coulombs of charge flowing through a wire length 3.6 meters in 6.25 seconds, and it's coming out of the page. So I'm going to draw a dot here to illustrate a wire that is hypothetically coming out of the page towards us. The wire is deflected with a force of 2.35 newtons upwards. So this wire that's kind of coming, I don't know, can I draw it like this? There's a wire coming towards us out of the page. Does that give you a decent 3D representation? This wire right here that's coming out of the page towards us is getting forced up. And the amount of force that it's being forced upwards with is 2.35 newtons. Our goal is to figure out both the direction and strength of the magnetic field. So first, let's say that we can try to figure out how to orientate our hand. I don't actually know which way to point my fingers, because that's kind of the point. But I know which way to point my thumb. Your thumb's coming out of the page, right? So orientate your thumb towards you. We need your palm to force up. So this is kind of awkward, but you need your palm to be pointing upwards. Your thumb out of the page, your palm upwards. Which way are your fingers pointing? Hopefully towards the classroom door. Awkward. What that means then is that there must be a south magnet over here and a north magnet over here. And that's what's going to cause this wire here to go upwards. Whew. These things suck, don't they? Okay, so our field is going this way. All right, now that we've done the theory, let's do the math for it. We just have a charge flowing in a wire. The formula for charge in a wire is either ILB, or we could also base it on the formula QVB. Okay. Well, I think we're being asked to solve for field strength. So if we're solving for field strength, I have two options. I could either make it the formula FM divided by IL, or I could make it the formula FM divided by QV. Okay. Now, I'm not actually going to solve this puzzle because I'm hoping that you guys are okay with the math at some point. I just want to show you the puzzle. Okay. Do we know the force? Yeah, didn't it tell it in the stem up there? Wasn't it 2.35 newtons? So this is 2.35. And this one here is 2.35. 2.35. We either need to know current and length, or we need to know charge and velocity. Do we have a current? No. This is a charge, though. See how that right there, that's a charge? Do we have a velocity? It's sneaky, but isn't this distance and time? If we take 3.6, a distance, and divide it by 6.25, isn't distance divided by time? Isn't that your velocity? So without me actually solving the puzzle, because, you typing numbers into a calculator is not physics. but hopefully you can see how you'd solve the puzzle. We have this velocity right here by just making it distance divided by time. We know charge, we know force. That's how we'd solve for a magnetic field. If it's okay with you guys, I'm going to move past that because we got other fish to fry here. Let's try this one. Let's say you have an alpha particle moving through a magnetic field. Let's figure out how much force it's going to experience. This is another more or less entry-level question. I'm not going to actually solve the whole question. Let's talk about how to solve it. You have an alpha particle. We could use the formula ILB, but that's if you have something running in a wire. We don't have something running in a wire. We just have a single particle. So let's use the other formula, QVB. We have a V, right? Looks like we have a velocity right here. We have a 23 Teslas. That can go right there. It didn't tell me a charge. But wait, it's an alpha particle. Do you guys know what an alpha particle is? Have we talked about this yet? Okay, if you've never heard of what an alpha particle is before, if you know a little bit about chemistry, it's helium. An alpha particle is helium with no electrons. Okay. Helium should probably have 2 protons for sure. It probably has 2 neutrons, and it probably has 2 electrons. It's a helium-4-2, except what you do is you rip off the electrons. We often write the alpha particle like this. It's the symbol alpha. We sometimes write 4-2 on it. The 4 meaning that there's 4 total subatomic particles, 2 protons, 2 neutrons. Okay? This thing has a +2 charge to it, basically. Well, if this thing has a +2 charge to it, we actually know its charge. Its charge is 2, 1.6 to the minus 19. Because 1.6 to the minus 19 is the charge of 1 charged particle. We have 2 of them. Well, that's not true. We have 1 particle with a 2 charge on it, that's all. Okay. You guys remember talking about 1.6 to the minus 19 being the charge of an electron? Well, an electron's the same as a proton. Just one's positive, one's negative. It's the same amount. We just need 2 of them because it's got the +2 charge. So that's how we would solve this puzzle. Throw the Teslas in here, throw the velocity in here, and throw 2 elementary charges in for Q, and that would be the force it experiences. Side note, hypothetically, if it asked us to figure out which way the force was going, use your right hand. Why are you using your right hand? Because it's positively charged. We really only use our right hand if we have conventional current, but like conventional current isn't even a thing anymore. Like it's only historical, right? We usually try to work with electron flow, unless you're an engineer. Some people still do, right? But this would be a great example of if you ever have a positively charged particle, this is the one time that positives can move. Positives can't move through a wire, but you can just have a random positive particle running around. I know that seems kind of strange because we haven't got to the quantum level yet, but trust me, we're going to focus on like electrons, on protons. We'll talk about like, say, a calcium +2. There's a little bit of chemistry overlap to it. So, all right, let's move on. Let's talk about this one right here. Let's say this electron was moving through this field. So an electron is shot towards this field. What's happening in this field, by the way? What does the X mean? Let's go into the page. Okay, so there's a field, which what that means is that Genet's room has a big south magnet in it. Because Genet's next door to me. Does that make sense? If the field is going into the page, there is a massive south magnet somewhere in Genet's room, and on this side of the wall over here, there must be a north magnet. And the field is then running into there. And the electron tries to run through this field. First, let's figure out which way the electron is going to get moved. Okay. It's an electron, so take your thumb and point your thumb towards the windows over there. Take your fingers, point them into Genet's room. Which way is this particle going to get deflected? Downwards. Okay. Hopefully you kind of followed that. Thumb is the direction of the particle. Field goes into the page. Downward is the way that the particle is going to get deflected. If this was a wire, the entire wire would move. It's an electron, so the electron moves. Now here's what's cool about that. This electron will actually start to bend in a circle. Okay? And the reason why is it's now going to undergo what's called centripetal force. I can't do like a full review in the time I have left because this is a long lesson, by the way. I'm sorry that it's so long. I apologize. But do you guys remember centripetal force, things that go around in circles? What's going to happen is as soon as this electron starts going downwards, because we recognize it's going to go down, well, now take that same hand that you have there. You were pointing your thumb towards the door. Well, now you have to point your thumb down. Well, now which way is your palm facing? towards the door. This is going to cause it now to want to go this way. But now you can't even rotate your hand any further. Now that it's actually going this way, now the force is going to want to rotate it back up again. This is the definition of centripetal force, where like it's going to start going in a circle. Long story short, we can actually calculate the radius of this electron's path. This electron will now start going in a circle, and there's sort of a radius to its path as it starts heading in that circular motion. Our goal is to find that. We then have to put two formulas together. One of the formulas is the centripetal motion formula, and the other formula is going to be the magnetic one we just discussed. Okay, I taught some of you this. I didn't teach all of you this, though. Does anyone remember the formula for centripetal force? Because it's not on your formula sheet. Yeah. It's mv squared over r. You did remember it. Okay, you remember part of it. This is the formula for centripetal force, and where it comes from is the formula ma, and acceleration in a circle is v squared over r. That is on your formula sheet. The v squared over r is on your formula sheet. If you then make it a force, you make it mass times acceleration centripetal. That's kind of where this comes from. So this is the formula for something going in a circle, and if you just have a random particle, you make it equal to qvb. So I'm going to build us a formula that looks like this. We have a charged particle, and because it's stuck in a never-ending magnetic field, it's going to keep spinning in a circle. Formula for the circle, formula for the magnet. I don't actually want to solve this anymore. We're going to come to this point in math and in our physics here where I'm going to show you how to solve the puzzle, and I'll show you where all the numbers go, but I'm not actually going to do the calculations if that's okay, right? The point here is just to know how to solve the puzzle. Our goal then is to try to figure out the radius of the electron's path, so we want to try to isolate for this r right here. How do you get this r by itself? Take mv squared, bring the r up over here, and bring the entire qvb and drop it back down to the other side. You're kind of cross-multiplying and dividing. Here's something really cool. So there's a velocity squared in the numerator and a single velocity in the denominator. We cancel them. And so we've now made ourselves a formula for radius. You would need to know the mass of your particle, the velocity of your particle, the charge of your particle, and the field strength your particle is stuck in. And you could then figure out how it's going around in a circle, basically. And then here's the good news. We have all that information. I'll just kind of walk through it here. Here is my velocity. Here is my magnetic field. It's an electron. So the mass of an electron, it's on your data sheet if you don't know. It's 911 times 10 to the minus 31. And the charge of an electron, just one charge, right? One negative charge is 1.6 to the minus 19. So we should, in theory, have the velocity and the field strength given. These two come off the data sheet. We should be able to figure out the radius at which this thing... if you're not overly familiar with circular motion and you want a refresher, can you chat with me? I'll do that like on a as-needed basis, because maybe you're not familiar with circular motion anymore. Okay, I promise we're almost done. I've got one example left and then kind of a lead into the next lesson. Let's try one last one here. Say an alpha particle moves towards that same magnetic field. Let's figure out the velocity needed so that the force of gravity balances out the magnetic field and the particle travels in a straight line. So one more time here. Here is a velocity right here. Now, what we haven't considered is gravity. Okay. Gravity is going to want to try to cause this thing to kind of pull downwards, right? But hang on a sec here. Didn't we say this thing was going to go in a circle like that? But I've changed it. I've now made it an alpha particle. What's the charge of it? How does an alpha particle work? It's positively charged. So when we're trying to figure out how it deflects, you take your right hand, point your right hand to Janae's room, take your thumb, point it towards the windows. Which way is your palm going? Upwards, yeah. So the electron would spin this way. The alpha particle will actually spin the other way. Here's what that means then. The alpha particle wants to spin upwards by a magnetic force, but wouldn't gravity be kind of trying to pull it downwards? Now I know an alpha particle is really tiny, but gravity still applies to it. So here's how I'm going to build this formula then. We want to make it so that the magnetic force that's pulling up is exactly equal to gravity that's pulling down. That's how I'm going to start building my formula. What's the formula for magnetic force? Q, V, B. What's the formula for gravity? Mass times gravity. And the question said, find the velocity needed so that the force of gravity balances the upward force. Upward force wants to pull it up. It wants to go in a circle like this. Gravity is going to pull it back down. We're going to try to make it just go in a straight line. Right? So to do that, make these two forces equal to each other and solve for velocity. To do that, your velocity would be equal to mg over qb. And I'm not going to do the math again, but let's just make sure we know where to find all these values. Mass. The mass of the alpha particle is on your data sheet, right? So get that off your data sheet. It's on there, by the way. Gravity is 9.81. The charge of an alpha particle is 1.6 times 10 to the minus 19. Because remember what I just said, an alpha particle is a 4-2 nucleus with a +2 charge to it. And I'm pretty sure it told us the field strength at some point, didn't it? Don't we have the field strength in like the question stem? Yeah, here it is. 113 to the 5. Thank you for sticking with me for so long. You see why I hate teaching this lesson? My students hate it, because it's hard. The math is probably actually the easiest part, compared to the stupid hand rules everywhere. That being said, the math can be quite challenging because it's likely that you're going to be asked to take the magnetic force and make it equal to a different force, and you're going to have to build your own formula. It just depends on the scenario. In this case, magnetic equaled gravity. In this example back here, magnetic can't equal gravity because gravity is pulling you down, and magnetic was also pulling you down. Right? They're not opposite to each other. But change this thing from an electron to an alpha particle, now they can be equal to each other. So. Okay, last thought, then I'm going to be quiet, rest my voice. All of this leads to our last topic, which we're going to get to next week. We discussed, to start class, the physics principles of how electricity and magnetic fields can be used to create motion. There are two really common applications of this. One is if you have an electricity and you have magnetic field, you can create motion. This is the basic concept of how a motor is created. And motors have fundamentally transformed the things we can do. As an example, like say the microwave that's back there, there's a small motor inside of it causing the circular dish to rotate. Right? We're not talking the motor inside like a car. It's a different kind of motor, right? But like, yeah, that's an engine, right? But like a motor that causes things to rotate, that's a very useful technological device. All you need is electricity and magnets. Okay. The other thing that we can do is that if we have a magnet, and we move that magnet around, we can create electricity. Right? You guys remember the station right here where you move the magnet inside of the coil of wire? We can make electricity. Windmills do that. We're going to talk later about how that's called electromagnetic induction. To me, that is the most important scientific discovery ever. That's my personal number one. Because if we didn't discover how to make electricity, we would literally still be in the dark ages. We'd be lighting our rooms by candles. We would be heating our rooms by wood stoves. Right? But as soon as we discovered how to harness the physics principle of motion plus magnets making electricity, that's changed our lives. So anyways, this is my precursor to the future lesson, because this is way more than enough for one day. So. Questions? Do you understand this? I don't expect you to. Can I say that right now? After 1 hour of me trying to show you this, I don't expect you to. So here's what I've done. Last thought, and then you guys can work on this. On Moodle, I'm starting to like doing this. I don't know. It forces you to practice something. Can you guys eventually, maybe not right now, but eventually, click on the lesson 6, moving charges and magnetic fields lesson? Okay. I'll start at the beginning here. I will upload this video in a little while, plus I have old videos in there. It's really hard to learn an abstract concept with someone just talking to you and looking at pictures. Right? We're talking abstract concepts. These are not easy to get, but you can rewatch the video. Maybe this will help, though. I've got some practice questions. These are old diploma questions that are about like what would happen at point P when there's a wire right here. Okay, so I've just got 5 questions, one on basically each topic we discussed. Can you guys try that? And then once you're done that, the last thing I want you to do, sometime in the next week or so, do a reflection so that I know what I can try to help you with. I really find the reflections valuable. I've even started messaging a few of you about them. Some of you got my messages about that, where you ask a question and I send something back to you. So can you try the moving charges in magnetic field reflection? And what I basically want you to do is, can you try to explain to me what you feel like you do and don't understand? And that way, if you don't understand something, then I can try to target my approach over the next few days. Sound good? Okay, that's all I got. You guys are kind of free to go whenever, so work on those 2 tasks. Thank you, everybody. I appreciate your patience on a very long lesson.